Let's pop the hood and look at the architecture. Scipy is organized into sub-packages, each dedicated to a specific domain. This modularity is key. You don't import all of Scipy, you import what you need. We have cluster for vector quantization and k-means. We have FFTPack for fast Fourier transforms, essential if you are doing any kind of frequency domain analysis in signal processing. Then there's spatial for KD trees and nearest neighbor queries, super important for geometric data analysis. Endimage handles n-dimensional image processing, allowing for filters and interpolation on massive image datasets. But it doesn't stop there. We have interpolate for smoothing out your data points with splines, and special for those obscure mathematical functions like Bessel or gamma functions that you usually only see in advanced physics textbooks. The beauty here is consistency. Even though these packages do vastly different things, they share a common interface style and rely on standard NumPy arrays for input and output. This means you can pipe the output of a signal processing filter directly into an optimization routine without any friction. It's this cohesive ecosystem that makes Scipy the go-to for scientific computing. You aren't just grabbing random libraries from PyPy, you are using a curated, integrated suite of tools designed to work in harmony. Understanding this structure is crucial because knowing where to look is half the battle in technical problem solving. You need to know that ODR handles orthogonal distance regression, while sparse handles matrices that are mostly zeros. Now, let's get technical with our first deep dive: integration. In calculus, integration is about calculating the area under a curve, but in computing, we deal with numerical approximations. The scipy.integrate subpackage is your best friend here. The workhorse function is quad, used for general-purpose single integration. The syntax is straightforward: integrate.quad f, a, b, where f is your function and a and b are your limits. But look at the code on the screen. We define a Python function, say f of x, and pass it as a first-class citizen to quad. Scipy handles the heavy lifting of subdividing the interval and applying quadrature rules like Gauss-Kronrad to give you an accurate result. It returns a tuple, the estimated value, and the estimated error, so you know how precise your answer is. But what if you have multiple variables? That's where dBl quad, TPL quad, and nquad come in for double, triple, and n-fold integration. Look at the example using a lambda function. We can define inline functions for our bounds, allowing for complex integration regions where the limits of the inner integral depend on the outer variable. This is incredibly powerful for physics simulations or probability calculations where you need to integrate over non-rectangular domains. You aren't just summing rectangles here, you are using adaptive algorithms that converge efficiently. If you're building a physics engine or a financial model involving continuous compounding, scipy.integrate is the engine room you need to master to solve those complex mathematical sequences and series.
Next up, linear algebra. If you've taken a course on this, you know it's the language of data. While NumPy has a linal module, scipy.linal is the superior choice. It contains all the functions in NumPy's version, plus many more, and it's often faster because it's always compiled with BLAS and LAPACK support. We're talking about fundamental operations like computing the inverse of a matrix using linal.inv or finding the determinant with linal.det. But the real power comes in solving linear systems. Look at the equation system on the slide. 2x plus 3y plus z equals 21, and so on. Instead of manually performing Gaussian elimination, we define our coefficient matrix and our dependent variable vector, then simply call linal.solve. It handles the numerical stability for you. And for the advanced users, we have singular value decomposition, or SVD. This is the backbone of dimensionality reduction techniques like PCA. Calling linal.svd decomposes your matrix into unitary matrices and singular values. This allows you to compress data, remove noise, or identify key features in high-dimensional datasets. Whether you are building a recommendation engine or solving partial differential equations via finite element analysis, linear algebra is the bedrock. Scipy.linal ensures that your bedrock is solid, fast, and numerically stable. Never write your own matrix solver unless you are doing it for a homework assignment. In production, you trust LabHack via Scipy to handle the heavy lifting of algebraic functions.
Now, let's talk about speed. We all love Python for its readability, but let's be real. It can be slow compared to compiled languages like C or C++. This is where the Weave subpackage comes in. It allows you to include C or C++ code directly within your Python scripts. This is a game changer for performance-critical loops. The documentation highlights two main functions, inline and blitz. With inline, you literally write C++ code as a string, and Weave compiles and executes it on the fly. This can speed up your algorithms by a factor of 1.5x to 30x compared to pure Python. It handles the type conversion between Python objects and C types automatically. Then there is Blitz, which compiles NumPy Python expressions for faster execution, optimizing memory usage and loop overhead. While I should mention that in the modern Python ecosystem, tools like Python or NumPy often replace Weave, understanding this concept is vital. It shows the extensibility of Scipy. It's not just a library, it's a bridge to low-level performance. If you hit a bottleneck where vectorization isn't enough, you don't have to abandon Python. You can weave in C++ to crush that bottleneck and keep your high-level logic intact. This hybrid approach is what allows Python to remain dominant in high-performance computing environments, giving you the best of both worlds, Python syntax and C++'s raw power.
That's it for today. We've covered the architecture of Scipy, mastered integration and optimization, solved linear systems, and even looked at how to inject C++ code for speed. If this deep dive helped you understand the power of scientific computing with Python, hit the like button and subscribe for more technical breakdowns. I'm BK, and I'll catch you in the next one.